Today we're looking at Virtual Width Networks, or VWN. Its mission is, well, pretty clear. It's all about delivering the huge performance benefits of wider model representations, but without the catastrophic quadratic cost that usually comes with just increasing the hidden size.
Exactly. This paper from ByteDance and Seed introduces a framework that I think very elegantly separates these two things. It decouples the representational capacity, what they call the virtual width, from the fixed width of the actual compute-heavy backbone layers.
And the mechanism is really interesting. It relies on something called over-width embeddings, managed by what they term generalized hyperconnections, or GHC.
Right, and the results, they're not subtle. For an 8x expansion on a big MOE A3.3b model, they saw optimization accelerate by over 2.5 times for next token prediction.
And even more for next two token prediction, something like 3.5 times.
Yeah, staggering 3.5 times. That kind of token efficiency is a massive, massive economic advantage when you're training these huge models.
It absolutely is. And this isn't just a one-off trick. It looks like they've defined a whole new predictable dimension for scaling, which they confirmed with an observed log linear scaling law.
So yeah, let's unpack the motivation here, because this really gets at one of the biggest bottlenecks in developing large models. We all know from the scaling laws that making the hidden dimension the model with bigger boosts performance.
Right. A richer representation leads to a better model. Simple enough.
But the moment you try to do that naively, just widening the standard transformer, you hit a wall. The complexity of all those matrix multiplications, the attention mechanisms, it all scales quadratically with that dimension.
So going from, say, a width of 4096 to 8192 doesn't just double your compute. It quadruples it for the dense layers. It's just prohibitive.
Completely prohibitive. It's why we have things like conditional computation, like mixture of experts. That was one of the big solutions.
And MOE helps with capacity by making the inner FFN layer bigger but sparse. But it leaves that core hidden dimension fixed. So you still have this information bottleneck, right? The representational fidelity per layer is still capped.
Which is exactly the problem VWN goes after.
Mm-hmm.
Their insight is so simple but powerful. If the quadratic cost happens inside the transformer blocks, why not just expand the representation outside of them?
And then just pipe a compressed version of the information through the fast, narrow backbone.
Precisamente. So VWN defines this expanded token embedding dimension, the overwidth embedding, or dollars. But crucially, the internal transformer layers keep their smaller fixed backbone width, dollars. The heavy lifting happens outside the main compute loop.
It's a great analogy. It's like having a 16-lane highway coming into a city. But the expensive central bridge is still only 4 lanes wide. You compress the traffic before the bridge and expand it after.
That's a perfect way to think about it. You maintain that rich representation at the margins where it's cheap.
But wait, if you're taking this huge virtual capacity, say 32,000 dimensions, and squeezing it down, doesn't that just move the bottleneck? Wouldn't those overwidth hidden states, the dollar, just blow up your activation memory during training?
That's a super critical question, and the paper really focuses on the efficiency of the connection mechanism itself. And that's where the generalized hyperconnections, or GHC, come in. But before we get to the GHC bridge, let's just quickly cover the components.
Oh, yeah.
So first you have the overwidth embedding itself, where the input token is enlarged to deal dollars. And then because that wide state has to eventually talk to the vocabulary to make a prediction, you need to map it back down at the end.
With an unembedding or reduce operator, just a linear projection at the output.
Exactly. And as you can imagine, with these massive expansion ratios, stability becomes a real concern.
I bet. So what do they do for stabilization?
They found that for the really big ratios, like 8x, applying group normalization right before that final reduce operator was essential. And they cleverly set the group size to be equal to the original backbone width, dollars. It just helps manage the scale of the information before it gets compressed for the final prediction.
That makes a lot of sense.
Yeah.
Okay, so the engine driving all of this is GHC. Let's get into it. This is the innovation that lets the narrow backbone leverage that massive virtual space.
Absolutely. The best way to think about GHC is as a kind of learned state management system that operates along the depth of the network. Conceptually, it's almost like attention along the depth axis of the model.
Oh, that's a powerful way to frame it. So the stack of layers is a sequence, and the overwidth hidden states are a kind of vertical memory, like a depth-wise key value cache.
Precisely. Before a standard attention or FFN module, GHC does a compression step. It maps the wide state down to the narrow backbone size. The backbone does its thing, computes the output, and then GHC does an expansion step, taking the output from back to $, to update that persistent over-width state for the next layer.
So it seems like GHC is unifying a few older ideas like hyperconnections and FRAC connections. What kind of control does that give you?
It gives you really fine-grained control over both the total capacity increase, that's the ratio, and the granularity of how that capacity is segmented, which is the fraction rate in dollars. They even built an adaptive layer on top of this, dynamic GHC or DGHC.
Dynamic, so it adapts based on the input, right? The compression and expansion matrices aren't static, they're conditioned on the current hidden states.
That's correct. It's a learned, input-dependent mixing strategy. But that flexibility, it introduces a stability challenge. How do you initialize a dynamic system like that without it just exploding?
Good question. How did they?
The key was initializing the dynamic parameters to 0. So the system starts off purely static. And those static matrices, A and B, are initialized with these specific structured patterns, a cyclic pattern for the expansion matrix and a block matrix for compression.
So you establish a stable baseline before the learned dynamic part even kicks in.
Yeah.
Smart. Now, let's pivot to performance, because this is where VWN really shines, especially when you pair it with multi-token prediction, MTP.
The synergy there is just remarkable. MTP is a training technique where you're not just optimizing for the very next token, but also for a sequence of tokens, an n-gram. It gives you a much denser supervision signal.
And it seems intuitive that if MTP is providing all that dense supervision, it would really leverage the expanded capacity from VWN.
That's exactly it.
Yeah.
MTP forces the model to learn these rich, short-range compositional relationships. And VWN gives the model all these extra representational degrees of freedom, that huge virtual space to actually store and model those dependencies. It's a massive positive feedback loop.
Okay, so let's focus on those MOE 3.3b results with the 8x expansion. When you say 2.5x and 3.5x token efficiency, what does that practically mean for a team training a big model?
It means huge savings. I mean, just imagine a training run that costs you 6 months and $10 million in GPU hours. If you can hit that exact same performance milestone using 2.5 times fewer tokens, you've effectively cut your training budget by more than half. Maybe you get it done in under 3 months.
And the data showed this wasn't just a fast start, right? The advantage actually grew over time.
Yes, that's a crucial observation. The loss gaps between the VWN model and the baseline kept getting wider even after 3 trillion training tokens. It really suggests VWN is delivering a sustained fundamental capacity benefit, not just a quick convergence boost.
Which then translates to downstream tasks.
Absolutely. On their Collection B benchmarks, VWN got a plus 2.16 point higher average accuracy. So the quality improvement holds up, the representation is richer, and it generalizes better.
Beyond just the performance numbers, I think one of the most satisfying parts of the paper was the systematic scaling behavior they found. They took a smaller model and just varied the virtual width factor.
Portal. This is so critical for planning. We've had scaling laws for data and model size, but now we have one for virtual width. They found the loss reduction follows this remarkably clean log linear relationship with that factor, $3.
So we have a new knob we can turn, and we know what will happen when we turn it. Why is having a predictable coefficient so valuable?
Predictability is everything at this scale. They fitted a coefficient of minus 0.00069. What that means is every time you decide to double the virtual width, you can reliably expect the loss to drop by about 0.00069. It lets you make rational trade-offs between virtual memory, training tokens, and data.
And the gains were huge. On one test, VWN OPS8 delivered a more than 4-point accuracy gain over the baseline.
Indeed. We should probably also touch on the ablation they did on the fraction rate, dollars. That variable basically determines how many segments the backbone width is split into before connecting to that virtual space.
All right, and it's a finer split, a larger dollar always better.
It seems to be scale dependent, but with diminishing returns. For the model they tested, the effect of dollars basically saturated once it got bigger than 4. Conceptually is about the fidelity of the connection, while Tollers is the total memory budget. You need enough fidelity, but beyond a certain point, making the pipe a little wider doesn't help much more.
Let's go back to that idea of GHC as a tension along the depth axis. If you think of it that way, you can see why it avoids the quadratic bottleneck. It's not token-to-token attention. It's layer-to-layer memory access.
Exactly. GHC is like a learned, fixed-cost, linear attention mechanism over that depth sequence. The transformation matrices are learning how to manage this vertical memory bank. They compress the important signal from the current layer and write it back into the persistent, wide-hidden state, making sure context is carried across layers at a minimal cost.
So what is the real cost? If the theoretical computation is low, how low are we talking?
Theoretically, it's incredibly minimal. It's mostly just proportional to the cost of layer norm and a residual add. Linear, not quadratic. Even the memory overhead for the activations during training, they estimated it was only about 8.8% extra memory in a typical setup.
That sounds like a no-brainer. A sub 10% memory hit for a 2 to 3x token efficiency gain. What's the catch?
The catch is all about practical deployment on current hardware. Those low overheads only happen if you can fuse a bunch of operations into single, highly optimized GPU kernels. But even then, when the activations get extremely wide, like with VWN by 8, where $dollars is up to 32,000, the I/O and memory access overheads start to become the real problem.
So it's not the FLOPs, it's the data movement.
Precisely. Just moving that much data around a distributed system becomes the new bottleneck, and it can start to outweigh the algorithmic gains.
Which is why the paper gives that reality check. While 8x is great for research, for production today, you're probably looking at the more modest 1.5x to 4x range. So, let's sum this up. VWN is a landmark paper. It successfully separates representational capacity from quadratic compute costs. It uses this structured memory system, GHC, and over-width embeddings to deliver incredible token efficiency. And it proves that virtual width is a new systematic dimension for scaling.
And this raises a really provocative thought, I think. The success of VWN suggests that the benefits we get from wider models come less from the quadratic complexity inside the transformer blocks, and more from the sheer expanded dimensionality of the embeddings themselves. That's where the capacity to store context lives. So if the core transformer layer is the fixed bottleneck, then the future of these architectures depends entirely on how soon hardware designers working on memory layouts, interconnects, HBM can catch up to unlock the full potential of these extremely wide but algorithmically cheap virtual representations.